Anyway, let's start with quantum communication on urban network, and I'll just try to focus on one aspect of that. And I see this, hopefully contributes a little bit to the topic of that conference here. Anyway, I'm going to talk about quantum key distribution based on entangled photon pairs, and try to focus on a few practical properties that we encounter in this exercise. We also work on single photon bandwidth engineering that would probably fit in the larger context of quantum communication that covers most of this presentation. I think the time is a bit short. So the vision we are having is how can we use an urban optical fiber network to most prominently do quantum communication based on quantum key distribution, but also connect that to quantum communication that communicates between different solid qubits or traditional qubits in the physics community. What you need for that is a transparent optical network, and we wanted to use an existing fiber network that we have in Singapore that's small enough to have basically a good transparency from A to B. So we are working on getting these interconnects in an existing fiber network working, and we have demonstration programs to get this on the way on top of an existing classical communication. And we sort of like the way we want to do this is essentially, let me just go back here, essentially use this 1300 nanometer band, because most of the traffic that is currently going on is running on the 1500 nanometer band or the C band. That's used for all the internet connections to every household here. So what I want to talk about is implementation of a QKD protocol based on BBM92 that uses entangled photon pairs, encodes the information and polarization of these photons, and we transmit that light through optical fiber. So that's what we do. As I said, we have a photon pair source or number of photon pair sources, fiber routing hardware, and the number of end users that can be sort of like connected to this photon pair source in this metropolitan network. And the wavelength we choose for this demonstration is the so-called O band around 1300 nanometer. One of the nice aspects of that is that as we heard earlier, you have a high transmission, or not as high as in the C band, but you have a low dispersion. So it's 1300 nanometer band is where you have the lowest dispersion for photons, and that turns out to be actually quite useful or necessary. We are working with an entangled photon pair source that based on spontaneous parametric down conversion, the CW pumped PPKdB crystal. That's a standard technique, and whoever wants to see the details, I invite to look at that particular paper. That's sort of like a similar source than what we have been using there. We basically separate two photons around 1300 nanometer with a wavelength division multiplexer. What you see, or what we see, a typical performance is sort of like light spectrum. What you see there is we take out one photon, signal photon on one side, and the idler photon on the other side. You can see it's actually quite wide photons that we are working with, around 20 or 20 to 30 nanometer wide. We look for polarization correlations. That's not particularly impressive, but it's good enough to establish a key within the standard protocol with the error correction there. Maybe the brightness of that source is we get about 60 kilo pairs per second in milliwatt of detected pairs. This is our sort of like test bed, or one of the test beds we were using. So here's sort of like an aerial photo of a university campus. We are sitting here, and we had sort of like a fiber loop around nearby town that was about 10 kilometers long. Typically, people promise about 0.2 or 0.35 dB per kilometer loss in that 1300 nanometer band. We observed about 7 dB loss. So be aware, if anybody sells you low loss fibers, a realistic fiber will always be worse. We saw temporal correlations is very technical, about 1.9 nanosecond long for these photon pairs sent across this loop, which is good enough to see correlations between these photon pairs and extract a key. That fiber had a polarization mode dispersion of nominal less than 0.1 picosecond. Practically, we inferred it has less than 0.2 picoseconds or so. This is sort of like a typical diagram, what that fiber link looks like, measured with an OTDR measurement. horribly technical with my slide here. Now, many of you will say transmitting polarization states to an optical fiber for quantum key distribution is kind of silly because the fiber wobbles along all the time. But it turns out that the actual deployed fiber is fairly stable. So this is a measurement over a few days when we inject a clean polarization state, and we see, record the Stokes parameters, and that's sort of like a very slow variation. So that gives us an idea that we can actually just compensate out any polarization drifts in an active way. And that's sort of like a quick snapshot of the whole setup. So we have a polarization entangled photon pair source. Then this 10-kilometer fiber, we do a polarization measurement on each of the sides, and in one of the arms we inject a polarization manipulation state to make up for this polarization drift in this fiber. This thing is based on liquid crystal variable retarders. We had 4 in a row, and we just use a qubit rate in the key generation to choose a proper setting and servo basically away the polarization drift we see there. And that there's a nice scheme that you can just servo away all the polarization drift of the fiber. That system loss of the whole thing is about 30 dB. So we, most of them are due to the detectors, and the fibers contribute actually only a small part, and coupling another small part. This is sort of like a small overview of how this polarization compensation works in a practical running scheme. So we start out with generating photon pairs, we receive them, identify them, and extract a key that starts out with a huge qubit, and then after a few minutes of finding the optimum with a particular algorithm, we arrive at a error rate that's small enough to extract a useful key after error correction. So that's actually a nice result. And if you just let this run for a while, then we kind of operate that on this 10-kilometer loops with a not great but useful qubit of about 6%, and we get a final key rate of about 100 bits per second. And you find more details in this publication here. Let me just see. Then we were a bit more ambitious and tried to bridge a 20-kilometer link between the 2 large universities or larger universities in Singapore. One is Nanyang Technological University, the other is National University of Singapore, where we are sitting. There's a dedicated fiber to this, and sort of like they told us, maybe you want to use this fiber to demonstrate that this works. We have a spin-off company that provided the equipment, and it turns out now this fiber is very nice because it's transparent between the 2 universities, but it's a non-zero dispersion shifted fiber. So that's actually not a fiber that has a zero dispersion at 1300 nanometers. Consequence of that is we had to push a bit hard and filter down the bandwidth of this parametric down conversion source, and we just about managed to get some key rate after error correction that's in the tens, around 10 to 15 bits per second. Nothing fantastic. The qubit was absolutely horrible, but this thing was running over a few days, 1 week without supervision at all. Doesn't sound very impressive, but it actually was a demonstration. Can this thing run without 5 PhD students tweaking the thing altogether? And the answer was sort of yes. This is just to give you an idea of the effect of a dispersion shifted fiber. The coincidences of photon pairs arriving at the detectors were stretching out of a time window of maybe 5 to 7 nanoseconds. What we get when we use a nice fiber that's not dispersion shifted is around 2 nanoseconds. That was actually what the system was designed for, but we still were able to recover some key. This is sort of like an overview. We can operate in these pure entanglement-based systems with somewhere between 10 and maybe 100 bits per second over realistic distances on realistic fibers, deployed fibers. We probably could push this a bit further when we had better detectors, and that's certainly enough to feed existing link encryptors to establish keys in a reasonably fast fashion to really encrypt the high speed data traffic. I guess I should have probably talked more about activities that try to connect solid state qubits, but I thought in 10 minutes this is probably a story I should tell at another day. If you want, I can maybe focus a little bit on this temporal compression. That's a short enough story, but maybe there's a good point to stop talking here. I have no idea what time it is, but I hope it's not too much overtime. I want to maybe post a little bit of an advertisement. We are hiring in various areas. Just contact us on this webpage or on any of the usual channels. I'm not sure how bad am I with timing.
Oh, you are perfect. I mean, we are so much on time now.
Okay.
It's wonderful. Given that we got a bit delayed, it's perfect.
Of course, I could, present stuff that absolutely does not fit into 10 minutes, but
we have an extended panel discussion later. Bulat contacted you already, I guess.
Yes.
So we would, be happy to see more.
Okay.
For now, I will just ask one of our three questions also, which is what do you see as a contribution of quantum technology to 6G networks? 6G
networks. So I have to admit, I don't really know what a 6G network is. Here people are busy talking about 5G networks. So I do believe that at least from the more downstream side, probably quantum key distribution will happen in some forms between data centers and eventually maybe between the different nodes that all our fancy gadgets like telephones and whatever will come in 6G will talk to. That's stuff I see coming. We need to probably understand a little bit better existing fiber networks, or hope that people deploy dedicated fibers, but you find remarkably large unwillingness on telecom contractors to put extra fiber down for quantum communication.
And you were saying, well, better technical or understanding on our side of the properties of the fiber could be helpful?
Properties of the fiber, I mean, yeah, it's fairly clear. You probably have to live with, I mean, we as a physics community need to really use the fiber that people have put in the ground, I guess, and that means we need to live with the fiber that exists. I don't think it's a big problem if you want to have microscopic systems talking to each other. So there you would typically use very narrowband photons that you don't really suffer from dispersion. But you have to choose these transmission windows that exist there, and live with the losses, and don't believe the losses they promise you when they sell you a spool of fiber. So they will always be larger. And these were the best fibers we sort of could find.
Okay.
Very technical, sorry.
First of all, thank you, Bulat. What is it?
Oh, so I was gonna, nice talk. Besides the polarization drip that you had looked at, did you have to adjust for the temporal mode match problems and in your big loop, or did they didn't arise?
No, that's not a big problem because it's just a simple time delay, and the synchronization you can do. I mean, we have an algorithm that synchronizes the local clocks on the receiver, so they're completely independent. But these photon both photons arrive with a fixed and stable time difference, and you just do a correlation of arrival times on both sides, and you can do this very efficiently. The main problem is not the absolute time difference that you can synchronize very quickly within a second or two. Based on the signal, so you don't need any fancy clocks there. What is a problem if the pulses, the single photon wave packets sort of like spread out due to dispersion, and then you have this uncertainty of a few nanoseconds, and then you can't distinguish noise from real signal anymore. That's what we were hit in this particular experiment. Yeah, this.
All right, thank you. Appreciate it. Thanks.
Okay.
I have a question. So how can you comment on the you mentioned an algorithm how to stabilize the polarization over the time? Can you comment on how this works, or?
So there are several ways how you can do this. the way we did it here, I mean, that is sort of Yicheng's work. You would find this, explained in this Optics Express article. So it's basically just a random walk. Sounds very silly. You have these liquid crystal retarders. Let me just show this picture here. So and they each of those guys generates a polarization retardation. They're rotated with 45 degrees with respect to each other. So basically, if you want, you have an X rotation, a Y rotation, an X rotation, a Y rotation in this space, and you adjust. Each of these plates can adjust how far you rotate. Now, in principle, you would be able to do this with 3 retarders, but if you use 4 retarders, you avoid what you would call a gimbal lock. So there's always a nice pathway to the local minimum of the qubit rate in our sense. And then we just do a simple search in this parameter space, 4-dimensional parameter space, to find the minimum. And there are several ways of doing it. And the way it was done there is we basically explore the vicinity of the current setting, try to get an idea where it's going down, and then follow the path down. So you can't do conjugated gradient, but there's several ways you can do this relatively reliably.
So it's basically
very fast.
Just a numerical algorithm that somehow optimizes the using these 4 liquid crystal retarders. Yes. I mean, I'm a little bit puzzled because usually we just use 2 liquid crystal retarders to produce any kind of polarization. I mean, yes. So I'm not quite sure why you need 4, but okay.
So you would because we don't know in which state this whole thing arrives. So 2 would that's the way these retarders work is it's just an adjustable birefringence. So it has a well-defined axis, and you at least the ones we had generate an adjustable birefringence with a given axis. And then I guess this would be sort of like equivalent of a lambda half, lambda 2, lambda 4, lambda 2, lambda 4 plate combination. That would be sort of like the simplest version we could work with this setup, or these bad ear controllers. I guess you use this often in optical fibers. They have 3 elements. We added another one because that avoids this gimbal lock you would find for some freak combinations. And your polarization transformation of a fiber can go through all kind of funny parameters, and you don't want to you find a singularity that you all of a sudden need to adjust your liquid crystal retarders around that singularity. That's why we use 1 more, but I think we need 3 elements in the first place.
I'm almost certain you only need 2. Because I mean, but depends on the absolute. So that you have different liquid crystal retarders with different total retardation, right? Yes. So you can have ones which have, let's say, 1 wave rotation or 2 wave rotation or something like this. So it depends on what kind of range you have. Maybe okay. Okay, so maybe too detailed now. Sorry.
Yeah. No, I believe. I mean, this needs to work for any state. Okay, so this needs not work. I mean. If you have a well-defined horizontal state, you can make with 2 retarders, you can make anything. But this needs to undo a transformation that's done in a fiber. So I'm not sure whether this can be done with 2 on
this.